Hi, this is the second part of lecture 14 of registers, and right now, this part two will discuss the universal shift register. So let's talk in general what we have discussed so far, and we said at one point we said that we have in terms of registers we can have a write shift register, write shift register. And let's take an example of that. So let's say these are the D flip-flops and they are connected as so, okay? And we can have as well as we indicated or we stated that we can have left shift register, and all what we need is just to reverse the connectivity. Okay, reverse the connectivity. This so you will end up with a left shift register. We talked about parallel shift register, where data get in and um, get out in just single cycle, parallel fashion. We don't need, in this case, we need 4 cycles to shift in the data. Similarly here, but here we just need 1 cycle and the data will be in. We talked about the operation when we had a signal called load, that we don't do anything with the parallel register and basically no change operation. Okay, so this is one more operation that we have seen the um, in the parallel register. And then the question comes in: can we have really a register that does all these 4 operations? And luckily, yes, we can. And we will refer to this as the universal shift register. And in general, the universal shift register consists of um, different flip-flops, or several flip-flops. Every flip-flop of them is connected as so. We have here the D input, and we will refer to this as DI because this is the ith bit, and you have the AI output. And then the input to this D flip-flop is really coming from a multiplexer. And this multiplexer is controlled by 2 signals, S1 and S0. This multiplexer has 4 inputs: input 0, 1, 2, and 3. And we will now see what those control signals mean. And so these control signals have 4 combinations, okay, which is the S1 and S2, 0, 0, 0, 1, 1, 0, 1, 1. And what we will try to do is we'll try to perform all these tasks. We'll try to do a right shift. We'll try to do a left shift. We'll try to do a parallel load. We'll try to do a no change. So what we will have here is that we say that if we have the input 0, 0, we want to have a no change operation of, or no change of the data of the flip-flop. So, which means this multiplexer, when with the selection is S1, S0 are zeros, we will have in this input right here, we will have AI. So basically, AI gets in, it goes, to AI gets in, it goes to DI, and AI here doesn't change. Now, if we have a 0, 1 combination here, we would like to do a shift and in the right direction. And we see if we do a shift from the right direction, notice that if this is AI, we would like to have the input comes in from AI plus 1. So you can see that this input here, if we have this combination of A, we would like to have this coming from AI plus 1. But what happens if I am doing I would like to do a left operation, which means that if I am here AI, I'd like to have my input coming from AI minus 1. Okay, so in this case, shift. If I'm doing a shift, let's assume we're doing a shift left, when the combination of the inputs, control inputs 1, 0, I'll have here at this input, I'll have AI minus 1, which is the output of the flip-flop on the right side. Now, what happened if I want to do a parallel load? Well, that's when I have input combination of, let's see, for instance here, input combination of 1, 1, and then I'd like to do a parallel load. This is where the third input here is going to have AI. So if I have a parallel load, this AI will go in, da 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 da, all the way to the flip-flop and the output. So you can see in the universal structure, let's talk about the main components now. First of all, I have this multiplexer, the mux and its control signals. And then the input of the mux are stitched in a certain way, okay? And then the flip-flops here. So these are the main components of my shift, of my universal shift register. Let's go and now to the notes, because we have a diagram, a nice diagram for us where it explains things beautifully. So here we have this. This is the universal shift register for 4 bits. Now notice that this is here flip-flop 0, flip-flop 1, flip-flop 2, flip-flop 3, and what we are having a universal shift register of 4 bits. And notice this is the multiplexer that we talked about. This is the multiplexer that we talked about. So let's take for bit I here, okay? Bit I here, I equal 1. So notice that this is here for bit 1 here, okay? Notice that this is D1 and this is Q1, okay? And we'll see that for this multiplexer, if I am doing, if the control signals are 0, 0, then notice where the data is coming from. We said that 0, 0 means no change. Notice how data will come here, all the way here. Notice, and immediately to input 0. So we're going to input A1 to B1, and that means no change. But notice when the control signals are 0, 1, then we say that we need a plus AI plus 1 in the whiteboard. So which means that for A1 here, you will see that this is A2 coming all the way, and oops, sorry, all the way right here. So you can see this is A2. Now for left operation for A1, we need A0. So you can see that here. Let's change the paint color here. Uh, so you can see that here, this is A0, comes in all the way here. And this is what we refer to in the whiteboard as AI minus 1. So for A1, this is the A minus 1, which is the A0. Now, when we have the control signal 1, 1, notice that we have the I input gets in and then B input. So by controlling the input of the multiplexer, notice how much operations that I have done. I have done a left operation, right operation, parallel load, or no operation. Now, one question is, notice that for these flip-flops that are in the at the edges, this flip-flop and this flip-flop. And so for this flip-flop, we don't have a previous flip or adjacent flip-flop on this side or adjacent flip-flop on this side. In this case, we will have to use a serial input all right, for the left operation, and a serial input for the right operation, because there are no flip-flops adjacent to me in this side or that side. So these are used whenever there is no flip-flop that I can take from it. So this is the serial input that I feed in for the left operation, and the serial input that I need for the shift right operation. Serial input for shift left and serial input for shift right operations. Okay, and now you can see that we have established this register, and you can see that how this operation of this register, or by changing control signals, I can change the operation of this register. We can take, for example, here an example. Let's say, for example, here, let's say we need, let's say, for example, a shift to the left. Okay, a shift to the left, and shift left is an operation where I have, this is 1 0. So I will activate all these inputs, right, to the which are at 2, for example. Okay, and you can see that now. Let me prior to compute the output, see what's a shift left. Well, if I am having my original register value is A0, A1, A2, and A3, and this is basically are stored in my flip-flops. Okay, and then I want to apply a shift to the left, then the result will be, after the shift left operation, will be this data is going to come here, and this data is going to come here. Okay, and this data. Okay, so this will be here A2, and this one will be A1, and this will be here A0, and this will be the shifted input, the shift input, which is from here. So this is what I expect from what operation? A shift left. Okay, let's see if my universal register does that. Okay, so now you can see that here I'm gonna have this shift input. So this shift input, okay, is gonna go all the way here and register, go to the register. So this is the shift input. Now, how about here? Well, here I'm going to have the A0, the input A0 is going to come over here all the way, and then it resides here, the value of A0. And then let's see here the value of A1. So here is the value of A1. So this is coming here. The value of A1 is going to go here all the way here to 2, and then it will reside here, the value of A1. Similarly, the value of A2 is going to come over here and to 2, and it will reside over here, the value of A2. So now you notice I have here what? The value of the shifted input, serial input for left operation, and then A0, A1, and A2, which is what I predicted in my computation for the left operation. Okay, and let's say for example if we do a right operation. Well, let's say for example if we do a right operation, this in the right operation will control will be 1 and 0, which means I'm going to take these inputs, right? So universal shift register, let's see, this is A0, A1, A2, and A3. Okay, so this is a register. Okay, so, oops, I'm sorry. Let's go to okay, let's do this one more time. So let's say, suppose I have A0, A1, A2, and A3. So these are the values of my register. And if I apply, this is one more time. Let's try to watch our okay. So A1, A0, A1, A2, and A3. These are the values in the registers. If I do a write operation, so which means in this direction, it will be A1 will be shifted here, A1, A2, A3, and I will have the serial input comes in here, and these are the values of my register after one shift, one right shift operation. Now, so since the control signals will be 0, 1, according to what we have discussed earlier, then I'm going to pick this input, this input, this input, this input, okay? And now, let's change color here. Let's say, for example, we'll use this. So from here, this will be what? This is the serial input. So, well, serial input comes in here. Okay, whoops, again. There's something not right in this presentation mode. Okay, so let's go here. Okay, so one more time. Okay, so this is 0. Okay, this is the first time it does this kind of flickering. Okay, uh, so let's oops. Okay, um, so this is here 0, 1. This is the serial input. We say that we're gonna pick the one inputs, the one. Okay, so the serial input here for right operation is going to come over here, go all the way to the D flip-flop. So this becomes the serial input as in terms of output. Okay, and then when the clock comes in, and then here, okay, for this one here, we'll have we said that we are doing what operation now? We were doing the right operation, the shift right. We were doing the shift right operation. Okay, so then we have this one here. The A3 comes in and goes all the way. So this is A3, and the A2 comes in here, and this is A2, and then the A1 comes in here, and this the A1. So the values of the register will be SI, A3, A2, A1, as we predicted, the value of the right shift operation. Okay, all right. So one last thing, one last point I want to mention. If we go to the whiteboard here, um, um, if we go to the whiteboard here, is that if I have a data, let's say for example, this is my universal shift register. If I have a data, and this is the data I want to shift this data to my universal register. The very first bit of the data that will be shifted, the least significant bit. And if I have the same data and I want to shift it into a left operation, then the very first bit that I want to shift in the register will be most significant bit. So in terms of serializing the input and the output. Okay, this is pretty much what I have for you for the Universal Shift Register, Lecture 14, and thank you very much.